All right. Without further ado, let's go ahead and get this started. As I mentioned previously, we are recording this today, so we'll post and we'll send around links for review later. So if you have other folks that may have missed today and you want to share, we'll have that posted. So without further ado, Ted Wilmus is up. I'll hand the microphone to you and have a great session.
Hi, thanks, Scott. So welcome everyone to our JanusGraph community meetup. I think this is the third time we've been doing this now. It's a good way to hear about what's going on in the JanusGraph community and learn new things if you're new to JanusGraph or maybe already using it. As Scott mentioned, my name is Ted Wilmus. I'm a data architect here at Expiro. Wanted to include a little bit of intro information for folks who may have not used JanusGraph before. If you want to go try it out yourself, here's a link to the latest release. And if you're kind of interested in what's coming up next in future releases, that's also captured up on GitHub. So whether or not you're an existing user or a new user, that's a good way to keep track of what's been going on in the community, what's upcoming. And of course, it's an open source project, so you're free to add issues and bugs as you run into things. So today we have two speakers. Bruno Barisa is going to start us off with a discussion of running multiple graphs within a JanusGraph installation. So using this JanusGraph configured graph factory. And then we're lucky to have Florian Grieskamp from GData, who's a big JanusGraph user. He's going to discuss a lot of work he's been doing around JanusGraph query optimization techniques. And then at the end, if we have some time, we'll probably do about 5 to 10 minutes of just general Q&A. So as Scott mentioned, feel free to ask questions at the end of each speaker's session, and then we can have just kind of a general grab bag of questions for, say, 5 to 10 minutes at the end. So with no further ado, I will hand this over to Bruno.
Okay. Can you see my screen, I guess, right?
Yes, perfect. Thanks, Bruno.
Okay, perfect. Hi, everyone. My name is Bruno Berizo. I will try to share with you what we learned using the configured graph factory to manage multiple graphs on a production environment, and what we learned about the feature. So this is my information contact. If you want to reach me at any time, please do. So I don't know, we are going to share the slides with the attendees, right? Probably.
Yes, yep, the recording and the slides will be available, yeah.
Okay, perfect. So there's a couple of links here on the slides, and also some good information for you guys if you want to try it later. So what we are going to discuss today is what is the configured graph factory and when it makes sense to use it, what are some use cases, how does it work on a overall approach, how this is the API working and how you use it on a service, for example, a microservice, and what are the pitfalls and the conclusions that we draw after using it for a good amount of time on a production environment. So we stress the feature and learn a couple of things that may make sense to share with the rest of the community. So the problem it solves. The core feature that the configured graph factory allows is to manage multiple graphs on runtime. So in a standard JanusGraph deployment, you set up the graphs on the config file before starting the cluster, and then that's it. You can't just go and change that. So the configured graph factory allows to dynamically create, drop, and configure multiple graphs using the Gremlin script. So some use case can be a multi-tenant graph solution. For example, if you have you need to create one graph for each client that is registered in a site, and you need to set specific settings accordingly, depending on the user, and you need to drop one of those graphs at some point, that is a perfect use case for this feature. Another use case could be create multiple graphs as part of an ETL pipeline. For example, if you have to concentrate multiple data sources on a pipeline and you end up spitting out a couple of graphs each time that the pipeline is run. So that's another good use case for the configure graph factory. So basically, it's any case where the life cycle of the graph is shorter than the life cycle of the deployment. So you need to create, drop, and configure graphs as a side process of the cluster configuration lifetime. So yeah, it's a factory class that allows you to dynamically manage the lifecycle of the graphs. It has like a template configuration that you set up to create the graphs. So it's ready to go after the first setup. So you can specify different configurations after that, but you can also have this template configuration to create graphs by default. So how does it work? This is an example of a common interaction with the configure graph factory on the Gremlin shell. So this is the crude API that the class provides. This is get graph names, list all the graphs that exist on a given time on the cluster. This prints the template configuration, the line 2. I don't know if you are seeing this correctly. On line 3, we are creating a graph using the template configuration, so storage in memory. By the way, the configuration is the same as any other configuration for any other graph, so you can set all the standard configuration settings that you set when you configure a graph using the standard files on the file system. So here we create on line 3, we create a graph. On line 4, we open that graph, and then in line 5, we just create a random vertex and get the vertex back as a standard graph. Then we list the graph again in line 6. And you see that the new graph is listed. We drop the graph on 7, and then the graph is gone. So this is basically how you interact with the configure graph factory. There are also other APIs that are not shown here, like creating a new configuration. But yeah, this is more or less how you interact with the feature. So to make this available to a cluster of JanusGraph, you need to set specific settings on the configuration. On the graphs section of the standard configuration, you need to set this key, configuration management graph, and pointing to a valid graph configuration. This configuration management graph is the graph that is going to hold the settings that you create on the configuration that you create with the API, the template configuration or any other configuration that you want to create. This is an example of how you can configure this configuration management graph. So it looks pretty much exactly the same like any other graph settings except for the graph name. And I think that the Gremlin graph is also configured graph factory. This is not standard, but the configurations are pretty simple. Once you have that set up, you need to create a template configuration. So you have like by default settings that are valid. So you need to use this create template configuration API and pass a map configuration to it. So here you can set any standard settings for a graph configuration. So this is not mystery. All the settings are what recommended on the docs. And this is how you create a custom configuration, a configuration that is not template. So the only difference here is that you need to specify the graph name. So when you create the configuration, you can open that graph by the name. But other than that, it's just the same. So this is basically how the feature works on the JanusGraph level, and how you configure JanusGraph to allow to use it on the Gremlin scripts. Then if you want to, if you need to access the feature from a service, for example, from a Scala application or from a Spring web service, you need to send Gremlin commands. There is no API, no native API to talk to the configure graph factory. So you need to issue commands by the client using the standard submit method to run Gremlin scripts on a remote server cluster. So this is an example of listing the graph names, but of course you can use any other script in this string. For example, create a configuration or drop a graph or whatever other API you can call. So once the graph is created, you can use a driver remote connection to access the graphs. And that is because every time you create the graph, the configure graph factory will add a traversal to the Gremlin context. So when a graph is created with the configure graph factory, an alias to a traversal source is added to all the context, all the Gremlin engine context on the cluster with the underscore traversal at the end. So for our example, we were able to use the user 123 underscore traversal source to issue Gremlin queries directly using that remote driver. So we can use the native API using this API to connect to the graphs. So I put an example of how a basic setup, so you can start playing with this on your machine without having to go back and forth with all the settings or just running everything locally. So I have a document compose here with a Cassandra and a JanusGraph already ready to go to. You just run document compose up, and you have configure JanusGraph ready to go with configure graph factory, and you can just play with the Gremlin engine and the API. It's also, there's a couple of examples there on the README, so you can just start playing with that. So the common pitfalls that we have. First thing is that we stress the feature on the cluster side of things. I think that this feature is ready to go if you're running on one node, but we are running on a multi-node cluster, and we quickly find that there are a couple of bugs that were causing some troubles to us. We already submit pull requests for both of them. One is already merged, the other one is almost there. Yeah, we found some bugs, and probably if you are thinking on pushing this in production, there are other edge cases that probably are not covered. Yeah, this was really battle tested on one node. The memory consumption can grow. I think that this is because you basically have one JanusGraph per graph that you are creating. So there are all the backend, all the storage layer is independent from each graph, and then can grow the memory consumption quickly. The operations over the graph, like create and drops, can be slow if you are using like Cassandra with probably 100 of key spaces. It can take like in order of probably 5 seconds, so something like that. So it's not like really fast. If you have a large number of graphs, it can take a long time to start, because when JanusGraph starts, it opens all the graphs that are available on the configure graph, on the management configuration graph. So if you have, like, for example, 200 graphs that happen to us, it can take like a couple of minutes finish open all the graphs and starting up all the storage layer for everyone. The cluster consistency can take, when you make a change on one of the nodes on the cluster, the changes can take up to 20 seconds to reach all the nodes. That's by design. This is not a setting that you can play with. It's just, it's like it is like that. And you need to be prepared, because it will, if you have, like, for example, an API that is using the whole cluster, the whole number of nodes, and you are issuing commands to one of the nodes, the other, and your application is using other nodes that you are not issuing commands to, you are going to have like missing graphs or seeing graphs that are already dropped. So you need to take that into account. So the conclusions that we draw after pushing that to production is that we will need the fixes that we push if you are planning to use this in production in a cluster, because you surely are going to hit the same issues that we found. So if you are thinking on using the configure factory in production, you should probably cherry pick our changes and build a custom core jar and run that, or wait for the open 5 version to come out. As I mentioned before, the inconsistency in the cluster can be a problem. So you need to think about that when you are building the application, or means to mitigate that, because it's going to happen. And when you're planning the resources, you should measure the number of graphs. The number of graphs can be a source of performance problems like I mentioned before, the memory and network, and also operations, because the size of things can grow really fast. So this is all I have. I missed the Q&A slide, so if you have any questions, just shoot it.
Great, thanks, Bruno. Yeah, if you have questions on this specifically, go ahead and submit them now, and then I'll read them out loud, and Bruno can answer them. Give folks a few minutes here to see if we get anything. Okay. Well, if you think of anything in the meantime, like I said, we'll have some more Q&A at the end, so feel free to ask then. I know we do have a few questions in here. Just to let you all know, I will get to these. I'm just going to wait till the end, so don't worry, we'll get those answered. Okay. Thanks a lot, Bruno.
Thanks.
Okay, at this point, I'd like to welcome Florian to present on JanusGraph query optimization. Thanks, Florian.
Yes, hello. Can you see my screen?
Yes, yep, looks good.
Okay, that's good. So hello, everybody. Nice to have all of you here. Let me first introduce you to myself. My name is Florian Grieskamp, and I'm working together with Jan Jansen and Florian Hockmann at GData in Germany. Some of you might know these two guys because of their involvement into the JanusGraph project. And for me, I'm using JanusGraph extensively as part of my PhD research on graph databases. And a core topic of my research is query optimization. Therefore, I'd like to use the opportunity today to talk a little bit about open potential in optimization for Gremlin and JanusGraph in particular. So I prepared a few animations. And let's begin with an optimization that is already part of JanusGraph since earlier this year. And this optimization focuses on efficiently handling neighborhood queries with respect to the storage layout on the backend side. And as an example for that, let's create a quick sample graph consisting of airports and routes. And each airport is represented by a vertex that has the properties city and code. And routes between airports are represented by edges. So we have a nice little graph here. And as you know, each vertex and each edge has to be represented somehow on disk. And to do so, JanusGraph assigns every vertex an ID. So every vertex gets an ID here on the storage backend. And to identify them later, each vertex is also assigned the properties that we chose, which are in this example, the city and the code. And what we have now is the representation of all vertices in form of a list. And this is actually exactly what's stored in the database. We have records consisting of columns for each property and each edge. But up to this point, we're still missing the edges. And as every edge interacts with two vertices, which are the incoming and the outgoing vertex, each edge needs to be stored twice, once for the incoming, once for the outgoing vertex. That is here for the first edge between Düsseldorf and Oslo. And we repeat this for every edge. And what we now have is our complete representation of the graph in exactly that form, how it's stored in the storage backend. We can now use this representation to have a look at a simple traversal and see how it is evaluated in the abstract graph representation and in the concrete storage implementation. So let's assume we want to find out if we can reach the airport of Rome, starting at the airport of Düsseldorf. And for simplicity, I am directly starting with the vertex ID 0 here instead of resolving the name first. And the first step of the query, V0, creates a traverser at the Düsseldorf airport, which you can see here represented by the Gremlin figure in the graph and in the storage. And starting from here, we can now iterate through the query steps one by one and see how they are evaluated. Next up is the out-E step. Notice that I'm using out-E in V, which is actually discouraged in Gremlin, but I'm still using it here for demonstration purposes because it's much easier to explain and to see the difference it makes. So the out-E step copies the traverser for each outgoing edge, which is in this case 5 times. So we now have traversers at these 5 edges. And notice that all data that needs to be accessed lies in close spatial proximity for the step. And that's always a sign that an operation is rather efficient, at least from a memory point of view. In contrast, if we look at the next operation, that is in V, it begins to scatter the traversers all around the database where entries can be really far apart. This is now one following each other one by one, but in large database, the traversers can now be scattered all across the database where vertices lie all across the storage. And the more connected vertices you have, the more inefficient this becomes. So that behavior is something that we want to eliminate everywhere it's possible. And to end the execution, Gremlin now moves the traversers to the vertices code property and drops all those ones that have values other than FCO. So we remain with only a single traverser, and that's the result of our query. But as I said earlier, we want to try to avoid costly steps. And so let's go a little bit back and see how we can improve the query execution. We are now at the point of the execution after the out-E step, where we have traversers at all the edges. And as I said earlier, we want to avoid scattering all the traversers across the database. So if we look at the 2 remaining steps, these are in-V and the has step. The has step does the filtering, the in-V step does the scattering. And what we actually want is to execute the has step, which selects traversers before the in step. And if you take a closer look, this is actually not possible out of the box now, because we are trying to filter on the code property, but the edges only have the vertex IDs. We can avoid this if we look at what the has step actually wants to filter. It's the code FCO, and we can do a lookup maybe an index lookup. And so by this lookup, resolve the ID of the vertex that we actually want. This is the ID 4. And we can use that in the query, rewrite it a little bit. So we don't filter for the code directly anymore, but instead of the filter by the ID of the adjacent vertex. And in the form that this query now has, we can simply drop 4 of the traverses right now, because we know they won't be beneficial for retrieving the result. We remain with only a single traverser and can now execute the inv step, which moves the traverser to the right vertex, which is the same one as before. And we're done. The query leads to the same result, but we don't need the scatter step, and we save much time, especially for large vertices. Because what looks now like a lot of work for marginal improvement can easily mean seconds versus hours of runtime on supernodes, for example. And that was the first part of my talk. That's something that's actually available now in JanusGraph since earlier this year. So queries in this form are optimized if there's a unique index available for the code property in this case. And for everybody who's still interested, I would like to introduce a different example now, where the use of this technique opens the doors for a wider range of more general optimizations. Just a quick disclaimer: this talk that's part of the talk that's now coming up is not part of JanusGraph right now. This is just theory and theoretical evaluation of what could be possible if we would have some kind of statistics backend in the database. So let's create a new schema as an example. This time we have a schema including companies and their stores and customers respectively. Now assume that we want to find all the countries in which there are stores of the company Apple that have customers named Bob. So we have companies, customers, and stores in our graph, where customers buy at stores. Stores are part of companies and are located in countries. How can we express a query like this in Gremlin? One way could be to have a look at the stores first. So we just do a lookup and take all the vertices that have the label store. And next we can exclude all those that are not part of Apple. Then exclude all stores that have no customers named Bob. And as a last step, look up in which countries they are. So we now have a query that answers our question, but one might now ask, is this a good query? And in particular, is this the most efficient one? We don't know. Maybe this form is more efficient. If we first filter out the ones that have no customer named Bob, and then do the filtering on the belongs to edge. This is actually hard to tell if you don't have particularly good information about the statistics of your data distribution. And therefore, this is a task that should be done by the database, not by the user. And at this stage of the optimization, we are now in need of something that database people call coast models, where we can put in a query and without executing it, an algorithm tells us how efficiently it will probably behave compared to other forms of the query, other execution strategies. So we can enumerate a large range of queries which all achieve the same but differently. And the ultimate goal is to algorithmically construct and choose the most efficient one. And to be honest, that's reaching for the stars a little bit, but we can still give it a go and see how far we can get. And that's actually my field of research, and I'd like to present one of the approaches that I came up with recently. So what I did is, first of all, we need, to understand the query, we need to parse an abstract pattern of the graph that describes what we are actually looking for. And to do so, I looked at the query and see that we are interested in stores that are located in countries. So we could have a pattern like this, a store which is located in some country. Next, the stores belong to the company Apple. So our pattern that we're looking for looks like this. And the next constraint that we have is that the store has a customer named Bob. So our pattern looks more like this. And finally, we want to select the countries. So this is something I will refer to as a pattern graph. And please keep in mind that this is not the data that's actually stored in the graph, in the database, but rather a pattern that we are looking for in the database to match data that's stored there and to return the results of the query. So now we can start with the optimization phase. And you might have noticed that I labeled all the vertices with labels A through D and edges with labels X, Y, and Z. And to start out, we can leverage some statistics to determine how many elements we will get from the database if we query for a single one of those vertices. So for example, starting at the country vertex, our database statistics may know that we have the label country about 200 times in the database. So if we query for only the country, we will get maybe around 200 results. We can do the same thing for the store. Let's say we have indexed 10,000 stores and continue with the other vertices. The vertex C, the company that's named Apple. That's a special case. We have a constraint here that the name is Apple. And maybe our statistics backend can now tell that we have a unique index on the name of the company. So we know that for sure that we will only get 0 or 1 result here. Let's go with 1, as this is the worst case. And lastly, the customer. Our index may now contain more than 1 result. Maybe that's 100 Bobs in the database. And now we have for each vertex an estimation of how selective the query of this vertex is. We can continue with the edges. And for the edges, we have always 2 directions of where we can achieve them. We can, for example, for the located in edge, look at how many stores we have. There are 10,000, and look at how many outgoing located in edges a store has on average. That's obviously 1 because each store is located in exactly 1 country. Or we can do it the other way around. Look at how many countries we have. That are 200. And look at how many stores we have in each country. I'm now going with 10,000. That is 1 located in edge per store because we have 10,000 stores. And we can do so for the other edges too. So for the belongs to edge, we have on the incoming side 10,000 stores. So this way around, we would have 10,000 belongs to edges because each store belongs to 1 company. And we could also do it the other way around and see that we have at the company C an estimation of the size 1. And we can now query our statistics backend to get an estimation of how many stores each company has. And if we maybe say each company has on average 10 stores, then we can estimate that going this way by the vertex C, we only have 10 matching edges for the edge belongs to. And for the last edge, we can maybe estimate that every customer buys at, say, 20 stores. So if we have 100 customers, each one buys at 20 stores, we're going to have 2,000 buys at edges. So we now have an estimation for each element of the pattern graph, but we can further refine them in the next round. For example, we know that the belongs to edge will only yield 10 results approximately. So we can refine our estimation of how many stores there will be, because we know that each belongs to edge has exactly 1 ingoing vertex store. We can refine that to 10. And propagate this refinement for the other edges and vertices. And by the time we are here, there are no more refinements that we can propagate. So the optimization phase is done. And we can now take one step back, look at the best ways to retrieve the elements, and look at how we got them. I wrote that in brackets behind the estimations. So we can now go through one by one. Take a look at the vertex A. We can achieve this with an estimation of 10 results via the edge X. And for every vertex and for every edge, do the same thing. Vertex C is a special case. We don't have a source here where we can get it from. So this has to be queried from the database directly using the index. Same goes for vertex D. And the edges X, Y, and Z can all be retrieved by their incoming vertices. So at the time we are here, we can now disassemble the graph into independent parts. That is first the left-hand side, where we need to query all the users that are named Bob and look at their outgoing edges by Z, which is particularly cheap. Remember the first part of the talk where we saw that outgoing edges of a vertex are in close spatial proximity to the vertex itself. So it's from a storage point of view, a very efficient query. And the rest of the query graph is on the right side, where we start at the company named Apple. We only retrieve one traverser from that and look at how many stores it has, move the traversers there. And from these stores, we have to join them with the stores that the customers buy from on the left-hand side. That requires a join step, which is currently not part of Gremlin, but that can of course be implemented. And lastly, when we have reduced the source to only those ones that have customers named Bob, we can continue to look in which country they are. And there we have it. We found the most efficient query plan to answer the query. And as I said, this is only pure theory right now. I implemented parts of it as a proof of concept, and the results look very promising. Well, at least promising enough to be confident sharing the idea with you. And I will continue researching this, so you can be assured to hear more about it once it has left the early stages of development. And until then, thanks for listening and enjoy the rest of the meetup.
That's great. Thanks, Florian. What are actually? You got me curious watching this. This is really cool. I was wondering, what are your thoughts on the statistics generation piece? Have you thought any about how that could potentially be integrated in a JanusGraph? Like, would it be kind of at write time or a asynchronous job, or what are your thoughts around that?
Well, most relational and even some graph databases are using statistics like that in a similar form. And I think graph databases can profit even more of such a thing more than relational databases, because we have relations between vertices and edges. We can store information about how many outgoing edges with specific labels a vertex has. There are things that are not possible as easily in relational databases. And updating those statistics is mostly done asynchronously in a relational database world. I don't really know about graph databases and how they do it. I think Neo4j does something like this, but I don't know how often the statistics are updated. In most relational databases, this is a query that is run by the user to update the statistics every time the user calls the function to update them. Mm-hmm. So this is left to the user. Maybe one could implement statistics that are updated on the fly every time the data is altered, but that would of course depend on how often you modify the data. If a graph database is mostly static and not often touched, that could be done without huge impact on performance, of course. But if the database is mostly written and the load is
Okay.
very write extensive, so then you would of course have a huge impact on performance on writes.
Mm-hmm. Yeah, that makes a lot of sense. Have you done any thinking about extending these sorts of these ideas to more recursive type graph queries? I could see how what you showed here could, of course, be embedded inside of a recursive, like a repeat type pattern. But is that something you've thought about at all, or any thoughts on that?
Well, at the current state, I reduced the number of available steps in Gremlin very much down to the most basic steps, like in, out, has, filter or something.
Mm-hmm.
I didn't even think about steps like aggregations like sum or average or something like that.
Mm-hmm.
That would of course have to be done. I don't know exactly how good they will optimize, but even if they are not optimizable at all, one could still disassemble the query and optimize those parts that are possible to optimize with this approach, and then reassemble the query and have at least a part of it optimized. That is still open research on how to optimize repeat steps, for example, or more complex steps.
Yeah, well, I think you're starting in the right spot, and this is already capturing some very common patterns. It also seems like this might plug in nicely to the match step, which kind of does a runtime optimization right now. But this, I think, could make some large improvements there using exactly the same techniques you're showing.
I'm actually using the match step when reassembling this pattern that you see now back to a Gremlin query.
Mm-hmm.
Then the optimized form, yes, that uses the match step.
Okay, great, very cool. Let's see. Anybody have any questions for Florian? Okay. Well, thanks, Florian. That was excellent. Really appreciate it. Okay. Well, thanks to both of our speakers. At this point, I think we'll open it up to some general Q&A here. We have 3 questions entered at the start of the call, so I'm just going to get started with those. If anybody else has JanusGraph questions, anything and all things related to JanusGraph, go ahead and put them in, and we'll work through those. Okay, so first one here is, could you please clarify if globally offline means you need to shut down the entire JanusGraph cluster at the same time, or you simply need to restart instances one by one until you restart them all? So what this is referring to here, if you haven't worked with JanusGraph before, or you're just kind of getting started, JanusGraph, of course, has a number of different properties that you can set that define kind of the behavior of the graph engine, or define where the driver is pointing at, just basically configuration parameters. And those parameters, each parameter has basically sort of a different level of mutability. So certain parameters you could change per JanusGraph instance. So if you had a cluster of 3 instances, each one could be running a different version of the parameter, or something like maybe a local cache size. Other parameters are global to the whole cluster, so every instance needs to be using the same value, and they need to be in agreement here. And so this particular mutability level here, this globally offline mutability, does mean you actually need to shut down the entire cluster except for one JanusGraph instance to change the value. An example of this would be the ID block size, which is the number of vertex IDs that are allocated at one time in a chunk to each JanusGraph instance. So in that case, to change that particular value, which is a very this would not be a frequent thing. You wouldn't need to be, turning your JanusGraph cluster off all the time. But if for some reason you needed to change this specific thing, what you would do is turn all of the Janus instances off except for one of them, change the value, and then bring the other ones up. So you still have one running, but the other ones need to be off. Okay, what is the cluster max partitioning and how do you increase the value in production considering it's marked as fixed configuration? So we just talked about this global offline. There's another mutability level which is fixed, which actually means it's immutable. So after that is set, you can't go and change it unless, somebody was to go get down into the weeds in JanusGraph, and maybe if this was a big enough issue that maybe there could be work done around making that a mutable value. In this case, this cluster max partitioning value though is actually immutable. You can't change it after it's set. It's set in stone for the time being. If this is an issue that you have a concern about though, for sure, put a issue in up on GitHub and kind of describe the specific use case and where you're running into the issue here, and then it can definitely be evaluated, but this is actually fixed. Why is JanusGraph using longs instead of UUIDs for vertices, edges, and how much effort would it take to add UUIDs to improve performance for high insert loads? So JanusGraph, for those who are new to JanusGraph, out of the box, the default configuration is set up such that all vertices have IDs, and the IDs are just longs. And those values are auto-generated by JanusGraph and assigned to the vertex IDs, or the vertices behind the scenes. Very, similar to say auto-incrementing primary key in a relational database. As far as why were they originally chosen to be longs, I'm not sure what the specific history was on that decision. I think though that this question is probably also getting probably to the point of maybe wondering if it's possible to assign your own actual IDs to the vertices as opposed to having to use the JanusGraph created ones. You can do this, but they also do have to be longs. So you could theoretically, that could be changed. I think that's probably a fair amount of effort though to make the self-assignable IDs to be UUIDs. I couldn't just off the top of my head really give an estimation on a level of effort there, but I think it would be fairly large effort. If you are experiencing performance issues though related to high insert workloads, I would recommend increasing your ID block size to a large number. You should still be able to get high throughput even with auto-generated IDs if your ID block sizes are large. I'm going to drop a link in the chat to a blog post. Let's see here, that has some more details around insert performance. Just one second. This has some sample settings in this area that you can refer to that may be helpful. I'm just going to put this in the answers here. So you can check that out. And then otherwise, for the meantime, if you do want to assign your own IDs without some pretty major changes, you would have to still map onto a long as opposed to UUID. Okay, so we have a JanusGraph configured graph factory question. I don't know if Bruno, if you want to take this one, but the question
Sure.
is, in a configured graph factory setup, are these configurations independent to each graph via the graph factory?
Yeah, the answer is yes. All the settings for each graph are independent unless you are using the template configuration that is shared between the graphs that are created using that configuration. So if you configure a graph, for example, to use the in-memory storage, using the create configuration API, and you want to create another one using also the in-memory storage, you need to create a template configuration with the in-memory storage, or create a new configuration with the in-memory storage. So they are not shared. I don't know if that answers your questions.
Yeah, Bruno, I think that was that was a good answer. So yeah, they can be totally isolated. Yep.
Okay, I will try to add a link to that, pointing to the settings, to the explanation, to the documentation, just for completeness.
Perfect. Great. Thank you. Okay. Let's see. Okay, so here we have a question about a specific pull request. Is this likely to merge anytime soon? The specific pull request in question has to do with allowing a custom edge ID. This one, I have name recognition of the pull request, but I'm not familiar with where it's at. So I couldn't tell you off the top of my head here what the status was of this particular pull request at this point. So it looks like it's had a pretty good amount of work on it, but maybe there's a little bit of more review going on here, although it appears to be fairly active over the past week, which is always a good sign with open source pull requests. So looks like it's in progress, but yeah, not sure exactly how long that's going to take. Okay. Anybody else have any other questions? Okay, great. Well, thanks again. Appreciate your attendance. We will get the recording posted and hopefully do another one of these JanusGraph meetups in a few months. And look forward to, oh, looks like we're getting some last minute questions in here. I'll answer these two and then we'll sign off here. Here's a configured graph factory one. When using the configured graph factory template, can I use a different Cassandra key space for each graph created with this template? Also, do I need to use the template when creating a graph?
Can I use different Cassandra key spaces? Yeah, you definitely are going to use one key space for each graph. So when you call the create method on the configure graph factory, that will create a key space for that graph. So if you create 10 graphs, you are going to have 10 key spaces. Also, I need to use a template when you create the graph. Not necessarily. You can use a template, so you don't have to specify all the settings each time, but you can create configurations independently for each graph. So the only, you need to remember to set the graph name so you can make reference to the graph once the configuration is created, so you can open, for example, or drop. But yeah, I think it's not it's totally mandatory to have a template.
Great, thanks, Bruno. This next question, I can't quite understand this next question. Maybe if you could re-enter it. Does the can adjacency currently be used?
I think that correct me if I'm wrong, Amy, but I think that adjacent makes reference to the Gremlin query that we saw on the presentation for.
Oh, excuse me, Florian's
Florian, yeah.
presentation. Yes, yeah, Florian, your first the first optimization you presented. Do you know what version of JanusGraph that got rolled into?
I also think this question refers to the first part of my talk. I don't know it off the top of my head, but I can quickly look it up.
Great.
Just give me a few seconds, I will look it up.
Yes, no problem. Thank you.
I will write the answer in the chat.
Perfect. Great. Thanks. Okay. Okay, well, yes, thanks again, everyone. And we will get this recording out and the slides. And if you have any questions, please reach out. And I'll give Florian here another second to post that version for you. The next, we got a question on when is the next release planned. There's usually not like a specific date determined until it gets very, very close to the final release process. The best way to just keep track of that and keep your finger on the pulse of it is to go and look at the milestone you're particularly interested in and just watch that percentage complete change. So that's usually your best bet. It's not going to be super precise, but that'll give you a good idea, at least roughly, how much is left to be done before before it'll be ready to go into a final release process.
There are multiple pull requests from my side that have to that together form this optimization. Some of them are merged in version 0.5.1, some are 0.5.2, some are also still open, I see. They are ready to merge. So everything with the first part of my talk should be available once the next version of JanusGraph comes out.
So yeah, so it sounds like probably, so a good chunk of it's in there probably in 0.5.2, but then the complete piece will be in probably 0.6.0, you thinking?
Yes, that's right.
Okay. Yep. So 0.6.0 is the one to keep your eye open to, and that's you can see under milestones the progress on that one. Okay. Well, thanks everybody for attending, and have a good rest of your day.
Thanks.
Thanks very much.